The objective on Mount Kologet is strictly defined. Investigators must document the resting condition of Convair B-36B Peacemaker serial number 4492075 under strict site controls, limiting disturbance to what permits and safety procedures allow. This remote peak in British Columbia holds the site of the first Broken Arrow incident. The stakes are entirely procedural. The operation requires mapping an extreme alpine debris field generated by a bomber that originally departed carrying a 10,000-pound Mark IV nuclear weapon. The primary survey constraint requires establishing the geographical boundaries of the fragmented wreckage, documenting hazards, and avoiding any large-scale recovery from the glacial environment. The constraint geometry of the heavy payload governs the initial threat assessment and the subsequent investigation. The Mark IV device carried aboard the aircraft was not armed with the fissile nuclear core required for a nuclear detonation. Official summaries describe a dummy capsule installed in the weapon, while later research points to a practice core rather than a live plutonium component. The immense payload still contained a natural uranium casing or tamper material and thousands of pounds of conventional high explosives, so the danger was never imaginary. But without the installed nuclear component, the weapon could not produce a nuclear yield, regardless of impact energy or structural failure at the crash site. The threat profile shifted away from nuclear yield and toward conventional explosive effects, metal dispersion, radiation screening, and component verification. The physical wreckage lies across the high-altitude slopes of Mount Kologet, where snowfields and glacial cover can hide sections for decades and expose others during seasonal windows. Access is governed by altitude, weather, isolation, and moving ice, making the mountain itself the practical survey boundary. The wrecked airframe went entirely undiscovered in this hostile environment until an unrelated aerial search visually spotted the fragmented aluminum 3 years after the initial loss. Positive identification of the wreckage established the location. The aircraft itself represented the pinnacle of strategic mass during its operational window. The Convair platform was an immense structure powered by 6 massive piston engines. When the bomber departed on its simulated combat strike mission, it carried a heavy payload and a crew of 17 men. The operational flight plan placed the aircraft high above the Pacific Ocean for a simulated bombing run. The historical and operational records indicate the aircraft encountered catastrophic in-flight failure over coastal waters. The ensuing survey and investigation must reconcile a profound geographical discrepancy between the last known flight coordinates and the final resting place. The documented bailout occurred over the Princess Royal Island area, above a freezing coastal maze of islands, mountains, and water. Yet the heavy bomber was eventually located on a remote mountain peak more than 200 miles from the bailout area. The prevailing account holds that the aircraft continued without its crew, but the exact reason it turned inland remains unresolved. Instead, it crossed rugged coastline and deep interior terrain, ending far from the ocean crash the crew expected. The debris field therefore reframes the loss as the terminus of an uncontrolled flight anomaly, forcing investigators to treat Mount Kologet itself as the central evidence problem. How did a heavily loaded bomber facing catastrophic mechanical failure navigate deep into alpine terrain uncrewed? The crew faced a rigid trade-off between a rapid descent and the retention of a classified payload. Keeping the massive weapon on board meant carrying a dangerous and secret device into an emergency whose outcome was no longer under reliable control. Dropping the payload became an urgent emergency action to reduce weight, protect classified atomic hardware, and buy whatever margin remained for an orderly bailout. The sequence of failure began in brutal cold. At Eielson Air Force Base, the ambient ground temperature dropped to minus 40 degrees Fahrenheit, and the bomber launched into weather that rapidly loaded the airframe with ice. Official summaries describe serious mechanical difficulties complicated by icing conditions. Later accounts attribute the engine crisis to icing and overstrained power plants. 3 of the 6 engines caught fire and had to be shut down. Whatever the exact internal pathway, the effect was immediate and catastrophic. Half the bomber's power was gone, and the crew was forced to manage a freezing, overloaded aircraft that could no longer hold reliable altitude. Operating on only 3 surviving engines, the bomber immediately lost its thrust symmetry and its ability to maintain altitude. The aerodynamic drag of the dead power plants forced the aircraft into an unsustainable descent. The crew calculated their remaining altitude against the rapid sink rate of 500 feet per minute. Every minute cost them 500 feet of clearance above the dark coastal waters. The crew opened the massive bomb bay doors, accepting the added drag long enough to release the weapon and cut the bomber's weight. That brief margin allowed the men to don parachutes and coordinate an orderly evacuation. The weapon released from the bomb bay and fell toward the dark waters off the British Columbia coast. Protocol required that the abandoned device not be left intact. Accounts differ on the exact moment of detonation. The official summary describes a bright flash on impact, while later testimony and research describe the conventional explosives detonating above the water. In either version, the blast scattered debris and uranium-bearing material into the ocean. Despite the reduced weight, the airframe could not sustain level flight. The crew reached an irreversible operational threshold. According to later testimony, the pilots tried to leave the aircraft on a course that would take it back toward the sea while losing altitude, reducing the chance that the abandoned bomber would strike populated terrain. This was an emergency control input made inside a crippled aircraft moments before the crew abandoned the failing machine. After the bailout, the wreckage shows the bomber did not continue into the Pacific. It turned inland, crossed the coastline, and reached Mount Kologet. Possible causes include autopilot error, a changed aerodynamic balance after ice broke away, or the unresolved possibility that someone remained aboard longer than surviving testimony can prove. The accidental discovery of the wreckage years later presented the military with a severe intelligence vulnerability. The aircraft still contained classified flight, bombing, and military equipment. The strict objective upon locating the site was to deny any exploitable technology to foreign intelligence. In 1954, United States Air Force teams finally reached the remote mountain terrain after earlier failed attempts. Their demolition effort focused on classified parts, especially the forward crew compartment and the bomb bay. Explosives and fire reduced much of that central wreckage to warped aluminum, while some aft sections and turret material remained more recognizable than the forward structure, with the airframe intentionally destroyed and heavily classified. What operational boundaries did the military impose when the wreckage was finally targeted for historical survey? The 1997 Hazard Survey required ground teams to navigate a dense field of volatile munitions just to establish a safe monitoring perimeter. Decades after the initial 1954 military operation, the debris field on Mount Kologet remained heavily contaminated with unexploded ordnance. Personnel conducting the environmental assessment faced severe movement restrictions. Scattered across the alpine terrain were live 20mm cannon rounds originally loaded in the defensive turrets of the bomber. Mixed alongside the aircraft ammunition were unexploded demolition charges left behind by the earlier military teams. This unexploded ordnance hazard governed every physical step taken across the remote site. The lingering danger of these volatile components dictated strict ground movement rules, meaning personnel could not simply walk the site or turn over metal plates without prior clearance. The primary objective of the 1997 expedition was to verify the environmental safety of the mountain. Canadian military personnel deployed directly to the high-altitude debris field utilizing helicopter insertion. Ground teams methodically swept the fragmented wreckage utilizing sensitive radiation detection equipment. The technicians monitored the scattered aluminum and surrounding sediment for radioactive material that might indicate a nuclear component at the crash site. The survey reported no elevated radiation readings and no high-level radioactive material in the areas examined. That result strongly supported the conclusion that the nuclear component was not present on the mountain, without requiring investigators to claim an absolute zero across every fragment of the alpine debris field. The ordnance findings were then passed to explosive ordnance specialists for disposal decisions. 6 years later, the 2003 Archaeological Survey approached the mountain with a different procedural objective. This expedition sought to document the site condition and locate surviving forensic proof of the payload release. However, the survey design faced a massive hard limit created by the site sanitization doctrine. That earlier demolition became a direct archaeological constraint. Obvious structural landmarks were gone, so surveyors could not rely on the standard crash load path to identify the central aircraft sections. High explosives tore thick aluminum bulkheads apart and threw fragments across rocks and ice. decades of glacial movement then shifted some pieces downslope into mixed clusters. The 2003 ground team designed its archaeological examination around these severe limitations. Heavy recovery equipment could not be used, and the work remained constrained by terrain, safety, and permit conditions. The researchers relied on visual documentation, surface measurement, photography, and limited artifact collection to map the primary debris field under established safety controls. The team identified lower fuselage structural clues and used them to build a controlled reconstruction zone with minimal movement of heavy debris. They used archival comparison only as a baseline for the more specific bomb bay search. At the center of the problem was the bomb bay itself. The area most needed to solve the historical record had been the primary focus of the 1954 demolition, leaving surviving metal twisted, burnt, and torn by forces unrelated to the initial mountain impact. Every technical assumption about the aircraft's impact condition was therefore clouded by destruction that followed 4 years later. How can researchers prove a payload was dropped when the very structure designed to hold it has been intentionally pulverized? To bypass this barrier, the archaeologists ignored the general shape of the wreckage and focused on specific components that still retained their manufactured geometry. Across the debris field, blast damage and glacial loading had obscured the original impact marks, but heavier mechanical parts could still preserve a usable forensic signal. The primary mapping effort focused intensely on identifying the structural boundaries of the bomb bay. Within the mapped debris field, the team used archival engineering blueprints to separate ordinary fuselage skin from the load-bearing girders of the central weapons compartment. Surveyors cross-referenced the shattered pieces against archival engineering blueprints to confirm the identity of the fragmented components. By methodically tracking the distribution of these thicker aluminum sections across the rocks, the surveyors reconstructed a rough perimeter of the internal payload area without physically disturbing the scattered metal. Within this specific structural cluster, researchers searched for the heavy mechanical components that interface directly with the payload. The deliberate explosive fragmentation meant most surrounding avionics and control cables were reduced to unrecognizable shredded material. However, the heavy-gauge steel of the primary suspension hardware inherently resisted the secondary blast forces. Amidst the warped and melted metal, the expedition documented remnants of the bomb shackle and related bomb bay equipment. This heavy hardware formed the interface between aircraft and payload. In an operational drop, the release mechanism opens and lets the weapon fall away under gravity, leaving a different load path than a mountain impact with the bomb still attached. Investigators therefore examined the shackle for stress signatures that would show whether the payload had been ripped from its mounts at the crash site. The surviving shackle was not pristine. It had endured fire, demolition, rust, and decades of exposure. But it survived in good condition, all things considered, and the investigators reported no evidence that it was holding the bomb when the aircraft hit Mount Kologet. That finding strongly supports the crew's testimony that the weapon had been released before the crash. The survey team documented the component in context, strengthening a historical record otherwise fractured by demolition, fire, and ice. If the shackle evidence supports the payload release, what forensic limits still prevent a full reconstruction of the bomber's final flight? The shackle evidence can confirm the payload release, but not the final uncrewed flight path. That boundary is set by the destruction of the forward aircraft sections. The primary missing component is the payload itself, now detached evidence far removed from the mountain. After the crew jettisoned it over coastal waters, its conventional destruction left no localized bomb debris on Mount Kologet, forcing the Alpine investigation to rely on surviving structural mounts and crew testimony for the release sequence. Beyond the absent weapon, the surviving debris field on the mountain presents a scattered array of detached evidence. The 1954 demolition and the original crash distributed material across a wide area of the slope. Pieces of engines, wing sections, and turret material were found far from the main wreckage, while some rear fuselage and twin 20mm turret assemblies remained relatively intact. This detached material vastly complicates any attempt at full structural reconstruction. Surveyors can document where a turret or turret fragment now rests, but they cannot always determine whether it broke loose during impact, demolition, fire, or later movement across snow and rock. This chaotic distribution leaves the inland turn as a verified outcome, not a reconstructible flight sequence. The cockpit section housed the primary navigation instruments and delicate autopilot linkages, and it was a primary target of the 1954 demolition. Investigators therefore lack intact controls, cable tension, flight data recorders, and measurable control surfaces that could show when gyroscopes failed or how asymmetric drag overpowered the aircraft. The shattered aluminum cannot yield that flight path data. This physical proof ceiling also extends to the human toll of the emergency. Out of the 17 men aboard the aircraft when the engines failed, 12 crew members survived the bailout and 5 were never recovered in the immediate search. The physical evidence on the mountain offers little reliable data to clarify their final moments. The historical record also contains a persistent discrepancy regarding whether every missing crewman left the aircraft. Some accounts hold that the missing men likely died in the icy waters between Gill and Princess Royal Islands after parachuting into the night. Other reports, including later claims cited by historians and witnesses, suggest that one body may have been found in the wreckage years later. Official reporting has not resolved that conflict in the public record because the relevant interior evidence was damaged, burned, demolished, and exposed for decades. The mountain site cannot settle that human contradiction. The exact fate of the final missing aviator remains unverified. The survey teams must operate within these verified limits. They map detached structural fragments and confirm the payload released through mechanical evidence, but the destroyed cockpit, scattered defensive turrets, and missing ocean debris prevent reconstruction of the bomber's final aerodynamic sequence. That limit defines the close of the forensic record. Is there a mandate to further investigate the wreckage, or does the mountain retain permanent custody of the debris? The physical window to observe Mount Kologet still shifts with the alpine environment. Receding ice can reveal some fragments while moving others downslope, so any future monitoring would depend on seasonal visibility and safe access rather than a fixed inspection schedule. Beyond the severe environmental boundaries, the site is governed by an absolute jurisdictional limit. The destroyed heavy bomber remains the official property of the United States military, yet the scattered debris field lies entirely within the sovereign territory of Canada. This international overlap creates a strict administrative firewall over the remote mountain. Any intervention, therefore, requires joint authorization between the two defense systems. Because the institutional objectives of identifying the wreckage and neutralizing immediate radioactive threats have been permanently met, neither government possesses a compelling mandate to alter the current condition of the debris field. The mutual sovereignty constraints effectively lock the site in a permanent administrative hold, ensuring the remote wreckage remains completely undisturbed by unauthorized recovery operations. The official management condition of the wreckage is better described as protected and permit-controlled, not simply abandoned or open for salvage. Current stewardship therefore centers on controlled preservation rather than recovery. The extensive explosive demolition conducted during the Cold War already reduced much of the central airframe to warped scrap, while the remaining debris carries historical value, safety hazards, and legal restrictions. Removing scattered fragments would require authorization, logistics, hazard control, and coordination with Canadian heritage authorities. The stewardship doctrine therefore leans toward documentation, protection, and selective authorized recovery rather than wholesale extraction. The fragmented debris is left in place unless a future government or permitted heritage decision changes that condition. The preservation of this restricted status is reinforced by the hostile alpine terrain itself. Mount Kologet creates a severe natural barrier against casual access. The geographical isolation, extreme weather, and steep slopes make any visit difficult, while the documented presence of unexploded ammunition and abandoned explosives adds a continuing physical hazard. Geography is reinforced by permit requirements, heritage oversight, and explosive safety controls. There is no public record showing a standing requirement for fences, sensors, or active mountain security. Unauthorized alteration or removal remains the line the legal framework draws. The technical investigation into the first broken arrow remains closed. Surveying archaeologists extracted the necessary proof from an intentionally scrambled debris field without expanding the disturbance footprint, leaving Mount Kologet as a protected, permit-controlled wreck site rather than an active recovery target.